In this problem, we have a penny drop from the top of the Empire State Building, which stands 380 meters tall. The question asks, how long will it take the penny to reach the ground? Let's start with drawing a picture. I'm just going to draw the penny here. All right, this penny's dropped. Let's draw the ground. And we know that it is 380 meters from the penny to the ground. We also know that if we just dropped it, we didn't throw it, we didn't toss it upwards, let's assume that it starts with 0 velocity. So that would be the initial velocity of 0. It's going to fall that distance, and when it strikes the ground, again, assuming no air resistance, it should gain a lot of speed. It's been falling for quite some time. This would be some final velocity. We'd expect it to be negative. We don't know what that is. What else do we know? Well, in order to gain that velocity and to fall that ground, it needs to get a push. That would be the acceleration due to gravity, which is going to be downward at 9.8 meters per second squared. And it's going to fall for quite some time, t, and we don't know what t is. For the sake of practice with position time and velocity time graphs, I'm going to draw a position time graph, and I'm going to draw a velocity time graph. When we deal with free fall, you tend to see a pattern here with these velocity time graphs, but I'm going to work through this one as it is. Starts at the top of the building, and it's going to finish on the ground. Right? At the top of the building, it has no velocity, so I can put a data point at 0 velocity. And when it hits the ground, it should be going really fast and downwards. We have a really steep slope, and therefore a steep velocity. And so we see that we should see a parabolic shape, where the slope is increasingly negative as the velocity gets bigger and bigger downward. And we should see that the velocity time graph should be linear, right? And the slope, because it is in free fall, the slope should be downward at 9.8 meters per second squared, the acceleration due to gravity. Remember, the acceleration is the slope of a velocity time graph. All right, next up, let's draw an ATVX table. All right, our ATVX table is what we use to organize the variables in the two equations we use. Right, equation 1 is our position function. Where it's located is 1/2 AT squared plus V initial t plus X initial. That's our parabola. And the second one is our velocity function, AT plus V initial. That's our line on the velocity time graph. So really we have our position time, velocity time functions, and let's put in our values. AT, V initial, V final, X initial, X final. These are our locations. All right, A is downward at 9.8 meters per second squared. That's always going to be the case if we're on Earth. If we change planets, well, then that might change and the problem would give it to you. But if it's not said otherwise, we'll assume we're on Earth. We don't know our time, and they ask how long. Well, that means that time is what we're looking for. I'm going to put a star on it. We start with no velocity, and we finish with some unknown velocity. I don't know what that is. I do know it's going to be negative, so it might be helpful to put a negative sign in here. Just for practice. And we're going to start at the top of the building. If the positive direction is up and we decide to call the ground 0 meters, then we start at positive 380 meters and we finish on the ground. All right, so now let's look at our equations and see what we have. All right, we do not have time. I'm going to put a question mark over time. And we do not have final velocity, but we have everything else, right? So I'm going to look in my equations here and say, well, is there an equation that has only one missing thing? Well, there's two missing things in each, but look at equation 1. The only missing thing is the same variable, t. And you're going to see something happen here with V initial. When it's 0, it'll actually simplify. But we can certainly use equation 1 to solve for time. All right, so I'm going to write out equation 1. I'm going to plug in the things I have in equation 1. My final position is 0. I have 1/2 of negative 9.8. I'm not going to put the units in here because I have everything in meters, seconds, meters. And so my answer should spit out seconds as an answer for time. So I'm just going to leave it just like this. Plus 0 times t plus 380, my initial position. Right, 0 times t just goes away, that's 0. And now we have an equation here that we can solve for t. You might want to simplify some things. What is 1/2 of negative 9.8? I can combine that, and I get negative 4.9 t squared plus 380. So I've just cleaned up my equation. I can combine 1/2 and negative 9.8 just by multiplying them. And now we're trying to solve for t. Well, let's get t by itself. I'm going to add 4.9 t squared to both sides to isolate t squared as a variable. That's going to eliminate it here. And I get a new equation that says 4.9 t squared is equal to 380. And now we want to get t by itself, or rather t squared. I can divide by 4.9 on both sides. And that's going to give me t squared is equal to, and I'll pull my calculator out, what's 380 divided by 4.9? And that is 77.55. Now be careful, that's what t squared is equal to. Well, how do we solve for t? Well, if we ever want to get rid of the square root, we have a function, or get rid of the square, we can take the square root of that. And if we do it to one side, you got to do it to the other. And so t is going to be equal to the square root of 77.55. So in my calculator, I can take that prior answer. I can say second square root. There's a square root function right above the square. You have to use the second or the shift feature. And I'm going to take the answer. So I don't have to retype it all in. It's going to take the square root of that answer, or I can type in 77.55. And I get an answer of 8.806. I can round that. T is equal to 8.81. And that would be in seconds, right? So we get an answer here. That would be the time it takes for that penny to fall. So it's going to be falling for 8 seconds. That seems reasonable. Well, it's a pretty tall building, and that's where it would fall. Now, some of you math guys might realize, well, when we take the square root of a number, you actually get a plus or a minus time. When we're going to learn how to find where these parabolas hit 0. This is actually, in math, the equation is not just this little piece. It actually goes this way. That parabola, this object, is going to be on the ground here. It's going to reach a final position, x final, of 0 right there. But if it actually was a complete parabola, this imaginary motion, it never happened. This wasn't on the ground before it got up there. But it would also technically have an intersection with the time axis, and because it's symmetrical, it'd be at -8. So that's where the math would suggest 2 different times, positive and negative 8.81. We would interpret and say, well, there was no time that existed before the penny was on the roof. It didn't get thrown from the ground to the roof, then back to the ground. So we can ignore that second root, or that negative time, and we get a positive 8.8 as when the penny reaches the ground.